Welcome to this video on bijections. This is a background video for a combinatorial technique called bijective proof. We are going to quickly review the terms injective, surjective, and bijective. Then we will talk about inverse functions and why having an inverse is equivalent to being bijective. Finally, we will talk about what these properties imply about the relative sizes of our sets. Our next video will be on bijective proofs themselves. Bijective proofs are very satisfying, and the definitions in this video provide the framework that we need to make rigorous arguments during those proofs. Here is our first definition. A function f from a set x to a set y is injective when different x's always map to distinct y's. Equivalently, if we were given two x's that map to the same y, then we were in fact given the same x twice. Intuitively, this means that every element in the set y is mapped to by at most one element in the set x. And I do want to note that the term one-to-one is a synonym for injective. So what does not injective mean? When we negate the previous definition, we get the following. There are two distinct elements in the set x that map to the same element in the set y. Let's move on to surjective. A function f from a set x to a set y is surjective when every element in set y is mapped to by at least one element in x. The term onto is a synonym for surjective. So what does not surjective mean? There is at least one element in the set y that is never mapped to. This brings us to the term bijective. A function is bijective when it is both injective and surjective. More fundamentally, a function f from a set x to a set y is bijective when every element in the set y is mapped to by exactly one element in set x. As we will soon see, there is a bijection between sets x and y if and only if these two sets have the same size. But first, let's talk about identity functions and inverse functions. The identity function for a set x is the function that maps each element to itself. In many ways, this is the simplest function defined on the set x. The official definition of an inverse function builds upon identity functions. Let f and g be a pair of functions, where f goes from x to y, and g goes from y to x. These functions are inverses of one another when f undoes g and g undoes f. More formally, this means two things. First, if I start with an element x from a set x, apply f, and then apply g, then I end up at the same x element that I started at. Second, this also holds for the set y. If I start at a point y in set y, and apply g, and then apply f, I end up back at the same y element that I started at. We have a special notation for the inverse function of f. We write f to the negative 1 for this inverse function. It's really important to note that both function compositions must result in the identity function in order for f and g to be inverses. This slide shows an example where applying f and then applying g result in the identity function on the set x. However, applying g and then f does not give the identity function on the set y. In particular, here is an element that does not map to itself. So in this example, the functions f and g are not inverse functions. They only satisfy half of the definition. So let's keep going with this idea of satisfying half the definition of invertible. Suppose that we have a function f from set x to set y, and a function g from set y to set x, so that f composed with g is the identity on the set x. We can make two conclusions. First, that the function f is injective, and second, that the function g is surjective. Let's prove this first statement. Suppose that we have x1 and x2 that both map to the same element in y. Now let's apply the function g to both sides of this equation. We know that this composite function is the identity function on the set x, and so we get that x1 is equal to the function composition on the left, and x2 is equal to the function composition on the right. And we can then conclude that x1 must be equal to x2. Our conclusion is that if x1 and x2 map to the same element, then x1 must be equal to x2. In other words, the function f is injective. Next, let's show that the function g is surjective by using a proof by contradiction. Let's assume, for the sake of contradiction, that g is not surjective. So this means that there is some element x in the set x such that g of y is not equal to x for every element y in the set y. In particular, let's consider the element y is equal to f of x. We can conclude that g of f of x is not equal to x, because f of x is just some element in the set y, and none of these elements map to the element x. This is a contradiction, because the function g, composed with the function f, is the identity function on the set x. Therefore, our assumption that g was not surjective contradicts a fact that we know to be true. We conclude that g must therefore be surjective. We have this lovely little theorem as a consequence. The function f has an inverse function if and only if f is a bijection. Why does this hold? Well, f composed with g is the identity function on the set x, and so the function f is injective. Meanwhile, if we flip the roles of f and g, we see that g composed with f is the identity on the set y. So this means that the function f is surjective. Now f is both injective and surjective, so it is bijective. And of course, its inverse function will also be bijective. Finally, suppose we have a function f from a finite set x to a finite set y. Let's see what these function properties tell us about the relative sizes of the sets x and y. This theorem gives us the whole picture. If f is injective, then the size of x is less than or equal to the size of y. We can prove this by turning it into a balls and boxes problem. Our balls will be labeled by the elements of x, and our boxes will be labeled by the elements of y. And we will place ball x into box y when f of x is equal to y. Now, if we had more x's than y's, then this function cannot be injective because we have to place more than one ball in a box by the pigeonhole principle. On the other hand, if the function is surjective, then we have to have at least as many balls as there are boxes. And finally, if it's bijective, then we must have an equal number of balls and boxes. This brings us to the you-try question for this video. Let's suppose that we start off with two sets, x and y, that we know are the same size. They both contain n elements. I want you to prove that in this special case, when the size of x equals the size of y, that if f is injective, then it must also be surjective, and vice versa. You could prove this result using the theorem on the previous slide. Good luck and have fun.